Lesson 9D, Tangents and Normals. Finding the gradient at a given point. So in the past few lessons, we learned about how we can figure out the gradient of a curve by making use of drawing tangents at certain points on a curve. And also, we learned a shortcut to find first derivative expressions and also evaluate first derivatives by subbing in the x value of the point of tangency into the derivative expression. In this lesson, this is an application of what we have learned about specific aspects of these curves, namely the tangents, which is the line that you draw at the point of tangency. Oops, it's not labeling right here. At the point of tangency on a curve. But related to the tangent is a line called the normal, which is perpendicular to the tangent. Okay. We will also make use of the facts that you have learned about slopes of perpendicular lines in grade 9. So if the slope of tangent has a gradient of f prime, then the normal's slope would be the negative reciprocal of f prime then, okay, just symbolically on this diagram, okay? So in order to find a gradient slope of a curve at a point, we really don't want to use the word slope of a curve, we use gradient. You substitute the x value of that point into the derivative function. So the tangent is the red line there. It touches the curve at one point locally. The normal is a line that is perpendicular to the tangent. So key point 9.6, the equation of the tangent at the point x equals to a is found using f prime of a. The coordinates of this point of tangency would therefore be a comma f of a. And then key point 9.7, the equation of the normal at the point x equals to a is found using the gradient negative 1 over f prime of a, and therefore the point of normalcy would be the same as the point of tangency, which is a comma f of a. So in most cases, we will find the derivative using the derivative rules that you already know. Well, so far we only learned one, but there are definitely more derivative rules that you're going to learn in chapters 20. But if we cannot find the derivative algebraically, your calculator, your graphing calculator is also capable of helping you to determine the gradient of the curve. Okay. Let's take a look at our very first example. So determine the equation of the tangent and the normal of the curve y equals to 1 minus 2x over x at the point where x equals to 2. Similar to the last lesson in 9c, we know that when the equation of a curve is given in this form, it's difficult to apply the power rule. But what we can do is rewrite the equation using negative exponents because the x in the denominator is a common denominator. So namely, we're really looking at 1 over x minus 2x over x, which results in y equals to x to the negative 1 minus 2. Okay. So let's take the derivative. We can either use the dy by dx notation or the y prime notation. We have negative x to the power of negative 2 minus 0. So we can skip that. Or if you prefer, negative 1 over x squared. Now, at the point where x is equal to 2, so we want gradient of tangent at x equals to 2, we're going to evaluate dy by dx at x equals to 2, so this is the notation, minus 1 over 2 squared, so this is negative 1 over 4. Since this is the gradient of tangent, therefore the gradient of normal would be positive 4. Okay. So let's move on because we're looking for equations of lines. So let's separate the section. We'll start by looking for the equation of tangent. Okay, so we're thinking about y equals to mx plus b form. For those of you who are familiar with something called a two-point form, a point slope form, you can also use that very conveniently. Okay, so maybe for the equation of tangent, I will find its equation using y equals to mx plus b. And then for the equation of the normal, I'm going to use the other form to show you how it works. Okay, so based on y equals to mx plus b, my slope is negative 1 over 4x plus b. And then because I also know that the I think I need one more thing before I can do that. I actually need the y value of the point of tangency. So let's go over to here, I guess. The y value would be y equals to 1 minus 2 times 2 over 2, right? You sub in x equals to 2 into the original equation. So what's this? 1 minus 4 is negative 3 over 2. Okay, so that's better. So now I can say that the point of tangency negative 3 over 2, negative 1 over 4 times 2 plus b. And then let's simplify this to find the b value of the y-intercept. So 1 over 2. So negative 3 plus 1 is negative 2 over 2, so negative 1. b is negative 1, and therefore y equals negative 1 over 4x minus 1 is the tangent. Okay. And then let's check out the other flavor of how we can use a point and a slope to find the equation of a line. In this case, is the normal. Okay. So this is point slope form. All right. So x naught, y naught represents the point on the line and represents the slope of this line. So y minus the y coordinates is negative 3 over 2. The slope of the normal we said is 4. And x minus the x coordinate is 2. Just like that. And so I have y plus 3 over 2 equals to 4x minus 8. And so y is equal to 4x minus 8 minus 3 over 2, or 4x minus 16 over 2, so minus 19 over 2. Okay, that's it. So this is the equation of the normal. Exam tip, IB exam tip. When you find some key information on an exam, you can put a box around those key information so that it's easy to look for them. Okay, so maybe that's important because you have the first derivative. Maybe the slope of tangent is important. The slope or gradient of normal is important, so the 4 here. And definitely your final answers, you can put a box around them. Oops, maybe my box is too big here. Okay. So let's take a look at another question. Find equations of the tangent to the curve y equals to x cubed that is parallel to the line 3x minus y equals to 4. Once you see the keyword parallel to the line of, you know that we're going to extract some information, which is the slope of 3x minus y equals to 4. Okay, we can easily do that by rearranging this equation. I have 3x minus 4 equals to y. So now this line is in y equals to mx plus b form. So therefore, the slope of tangent must be 3. Okay, the same slope as this line. That's good. So now let's figure out an expression for y prime, or dy by dx. Well, since y is equal to x cubed, then dy by dx is 3x squared. So let's set this equal to 3. So x squared is equal to 1, which means that x must be plus or minus 1. Okay, so that means there are actually two tangents that we're looking for. One at x equals to -1, and the other tangent at x equals to 1. Just to give you a quick overview of why this is the case, let's sketch the graph of y cubed. Many of you might be familiar with it already. So the sketch of y cubed, the function, looks something like this. So at x equals to 1 and x equals to -1, if I sketch in a tangent at these points, you'll see that both tangents would have the same slope. Okay. All right, so one at a time. And I know that because the function is y equals x cubed, the coordinate is 1, 1 and -1, -1 at the points of tangency. Okay. So that's good. So at x equals to -1, we can say that the equation of the tangent is y minus -1 equals to 3 times x minus -1 using point slope form. So 3x plus 3, this is plus 1, so minus 1. So we have 3x plus 2. That's the first equation. And then at x equals to +1, using point slope form again, y minus the y coordinate is equal to the slope 3 times x minus the x coordinate. So the equation of the tangent is 3x minus 3 plus 1, which is 3x minus 2. Okay, so once again, exam tip, put a box around your final answers. All right. Moving on, example 3. Find the coordinates of the point at which the normal to the curve y equals to -x squared at x equals to -1 meets the curve again. Okay, so what does that even mean, right? Maybe we'll let the picture speak 1,000 words. So imagine that you have a y equals to -x squared graph. I'll do it on the right side here. Well, it's going to be this function. It's a parabola that opens down, touching 0, 0, right? When x is -1, so somewhere here, the question says the coordinate point at which the normal to the curve at this point. So that means that I'm going to draw a normal line to this curve. So that extends somewhat like this, and then meets the curve again. And because I can extend the parabola as much as I can, and I can extend the normal line as much as I can. How come they're not touching yet? Okay, we'll fake it. Okay, so imagine they touch here. So basically we're looking for this point of intersection, meaning the equation of the normal has the same x and y coordinate as the equation of the parabola. Okay, so now we understand what the question is asking us to do. We should proceed to find the equation of the normal first. Okay, but in order to find the equation of the normal, I have to start with the slope of the normal, thus the slope of the tangent. Okay, so first let's find dy by dx, slope of tangent, -2x at the point x equals to -1 So I have negative 2 times negative 1, which is 2, which implies that the slope of the normal is negative 1 over 2. Okay. So the next step we said is to find the equation of the normal. Do we know what point this normal is drawn at? Well, we know that at x equals to negative 1, y is negative times negative 1 squared, which is negative 1. Okay, so this is negative 1 on the diagram. Okay, all right, so y minus negative 1 equals the slope negative half bracket x minus negative 1. So y plus 1 is negative 1 over 2x. This is plus 1, so minus 1 half. So minus 1 from both sides of the equation. I have negative 1 over 2x minus 3 over 2. Okay, so this is the equation of the normal. It's somewhat useful, so let's put a box around it. And lastly, we're back to trying to answer the question, right? We're looking for the point of intersection between the parabola and the normal line. So we're going to set equation 1 equal to equation 2. So negative x squared is equal to negative 1 half x minus 3 over 2. This is 0 equals to x squared minus 1 half x minus 3 over 2. I don't like those fractions, so let's multiply both sides by 2. I have 0 equals to 2x squared minus x minus 3. Okay, let's see if this is factorable. So the product is, I'll do on the side. So product is negative 6, 2 times negative 3. Sum is negative 1, so 3 and 2 would work, correct? So here we can do 2x, x. I need negative, so let's do 3 here and 1 here. So that negative 3 plus 2 would add up to negative 1. So the factored form is 2x minus 3 times x plus 1. Meaning that I can actually have a point of intersection at x equals to 3 over 2 or x equals to negative 1. So the x equals to negative 1 we already know, which means that the POI will occur at x equals to 3 over 2. So let's put a box around this because this is important. And then so we say this up. X equals 3 over 2 into the easier equation, probably equation 1. We have y equals to, negative 3 over 2 squared. This works out to negative 9 over 4. Which kind of makes sense if you look at the diagram, look at our sketch, and therefore the POI is 3 over 2, comma, negative 9 over 4. Okay? All right, so example 4. Given y equals the square root of x, use technology to find the slope of the tangent at x equals to 9. So first we can do this by using graphing. So if you press y equals on the calculator and enter square root of x into an equation, you can then press graph. And then the slope of the tangent at x equals to 9. So there's a calculate menu, so second trace, and then calculate number 6, dy by dx, and then you can enter the x value, which is 9. Let's see if my window fits that. Now you're going to get an error message if your window is not showing the proper range or proper domain where you need to do the calculations with. So I'm going to adjust my window from -1, I guess, to 10. And then I can ignore the rest, but I'll set it up more properly. So let's go down to maybe 5. And then let's try that again. Okay, so second trace. And then number 6, enter 9 as the x value. And there you go. Okay, at the bottom of the screen, you're going to notice dy by dx is equal to 0.1667. Okay, it's rounded. Now, if you don't want to do it using the graphical way, you can go to math, and then you notice number 8 is n derivative, and then you can enter dx, and then place the expression in their second function. Square root of x is the function that we're looking for, and the x value is 9. Enter, and you get the exact same result. Okay, so 2 different ways of doing this question. So either way, I'm going to record in the notes, which I will post in a Google Classroom, that using technology, dy by dx when x is equal to 9 is equal to 0.166 ... Okay. Next, we're going to take a look at part B of this example. So it says that we're going to look for the x-coordinate of the point on the curve where gradient is actually equal to 0.5. We're going to take a look at how this can be done on your graphing calculator. So type in the function square root of x into y1. So this is your original function, which we already have. And then in x2, we're actually going to graph the derivative of square root of x. This can be done by going to Math 8. So we enter the derivative expression. So dy by dx, and then the y, because the equation is square root of x. So you either enter square root of x, which is not complicated to do so in this case, or notice that your calculator has actually stored. So pick the variables button, scroll over to y-vars, one function, and then we're going to call this your function, derivative of the y1 function. Okay, and then scroll over, because we're doing the derivative function in general, we're not specifying an x value, we just enter x here. In y3, we are actually going to plot the value of the gradient, which is 0.5 in this case, that we're looking for. So imagine, I am looking for when the gradient function is equal to 0.5. So we will solve the system of equation graphically. If you like, because the first function is actually irrelevant, so we can actually scroll over to highlight the equal sign to turn off the graph, and then press graph. I know this is a little hard to see, so why don't we adjust the window to say -1 to 2, and then y min to maybe -1. We were like in the very short range there, so maybe 4, let's see. Much better, right? So clearly there is a point of intersection right there. And of course, we can use second function trace, which is the calculate menu, to find the point of intersection between y2, enter, y3, enter. Guess the point of intersection is 1, 0.5. Okay, so when x is equal to 1, the gradient of our function is 0.5. So let me record this in the notes. So I can write from the GDC. Okay, on the IB exam, you will have to show a sketch of the graphs that you see. So let me do that. So here is the derivative function. And then we also have our second function, which is y equals to 0.5. And then we will mark off the point of intersection is 1, 0.5. And therefore, x is equal to 1 when the gradient is equal to 0.5. Okay, so we have done this graphically. Okay, let me put a box around it. And that's it.